Hey everybody, so I'm going to go through what's called tree generation today, and the reason you would use tree generation for a sequence of tasks is that it describes all of the possible options of the sequencing of these tasks, and when you do all possible options, that inevitably leads you to getting the optimal solution. So that's the main goal of this tree generation. This can be found in slide 24 and beyond of Serial Systems 1. Also, it mentions here that if you have n tasks, then you would therefore have n factorial sequencing, and that's basically each individual branch of the tree that you would then generate. Also, this fable is basically using tree generation, but you would have some constraints, and therefore these fathoming rules, which basically make it so that you don't have to continue each branch of the tree if they go against your fathom constraints. So let's take an example where we have 4 tasks, and that would then have 4 factorial number of possible sequences. And the way we would go about drawing this tree generation is we would start with all available tasks. So in this case we're not going to have any precedence constraints, so all 4 tasks can start at the same time. We can simply label these 1, 2, 3, and 4. And then to create the tree we would simply draw all the next tasks. So let's say that we put 2 first, and then we would continue to 3 and 4. And then we can branch off of 2. We can put 4 first, and then 3, and so on and so on. So then this would have 3 and 4, and we would continue this for all of the remaining tasks. And this style of tree formation is called depth first, in which you generate the whole first branch, and then you go back to where it's possible to diverge, which would be here, and you would diverge, and you would go back and diverge again. That's called depth first. The other way we can do tree formation is we can do what's called breadth first, and that is a case where you fill out all of the remaining options for each first task. So you would draw all of the options here, and then you would do the same for 2. So you would have 2, 1, 3, 4, and then after you go through all of the first options, then you would go here and you could do 3 and 4, and you would do that all for the second group, if you will. Basically you expand each original node first, and then so basically you would complete all the final nodes, all the leaves, at the exact same time, instead of finishing the whole first branch and then the second branch, so on and so on. So the first method in which you complete the first branch is called depth, and the second is called breadth. And the main difference is the way you visit each node visitation. So in the first way we would have visited this node first, then this node second, and this node third. Whereas in the breadth situation we would have visited this one first again, this one second, but then we would have visited this one third instead of this one, as we would have gone down and expanded the first one. So it's this difference in node visitation sequence that changes between the two. So far we've decided to not use any constraints or fathoming rules, In this current example, we are going to provide the fathoming rule of precedence. So you can see here that C is preceded by A and B, and so on and so on. And we are also given our cycle time, and you can see the precedence chart right here. And so when we do our tree generation, we only have to do the ones that are actually feasible with these precedence constraints. So you can see here that we only expand A and B because those are the only ones that can start at this time. And then we would go on to the ones that are only able to, that only have precedence of A, and you can see that that is B and D, as C also requires B first, so we can't do that one first. And we would do that for all possible options. Another useful point of this method is that we can quickly see if one of our options is optimal by equating it to the lower bound. So if we sum up these right here, we would get 11, and if we divide that by our cycle time, we're going to need a minimum of 3 stations. And so you can see here that this option right here, which is A, B, D, C, E, fits within that lower bound. So we have our first station at A, our second station, which would be B and D, and our third station, which is C and E. So we could easily stop here and conclude that this is an optimal solution. Whereas if we continue on, we'll see that there are other optimal solutions, including this one, which is A, B, D, E, and C. But this is just chosen to place outside the fourth option as it is equivalent to this one. So we want to show the broad variety of options. Next, we're going to talk about mixed model assembly, and this is the idea of producing two different parts that are moderately similar on the same line. And so you can see here that they have similar work elements that need to be done for each of the two parts, and then the designated time that each of these work elements requires from the individual parts. And you can also see the precedence constraints for both. And so if we put this into a table, we can see that this is for part A and this is for part B, and this would show the completion route. And the idea is that we want to aggregate them into one flow. And so here we've done that by combining those that are required for both and placing them here. So you can see that all of the ones that say A, B are ones that are required by both A and B, and then you can see the ones that are only required by A and only required by B. And when we do that, we're going to need to calculate the aggregate time that's required at each of these areas. And the way we do that is we compare the ratio of how many parts are required in the work cycle. So if we go back here, we can see that A requires 4 units per hour while B requires 6 units per hour. And so if we use this in our ratio, we would have part A requires 4/10 of the work and B requires 6/10 of the work. And if we want to compute the aggregate time for, let's say, area 1, which has 3 for part A and 3 for part B, we would simply multiply 0.4 times 3 plus 0.6 times 3. And this obviously just equals 3. But if we take one that requires 2 different times, such as work element number 4, we can see that it takes 6 minutes on task A, or I should say part A, and 5 minutes on part B. And we would do the same thing. We would multiply 0.4 times 6 and add that to 0.6 times 5. And that would equal 5.4. And we can use this aggregate time to then balance the workstations. We should also note the way in which these parts would go through the line. So let's take another example and say that we have 3 parts that require production on the same line. We'll say parts A, B, and C, and they are required at 20, 40, and 50 per hour. We would then see what the common denominator is, which would be 10. We would divide all of these by, we would divide the demand by 10, so we would have 2, 4, and 5. And this would create our sequence, so we would produce 2 of part A, 4 of part B, and 5 of part C, and then we would repeat 2 of part A, so on and so forth, until we have our demand satisfied. And this would give us 10 cycles until we complete our demand. The last thing I want to talk about is parallel workstations, and the reason we would want to do parallel workstations, in other words having the same workstation but 2 of them, is that sometimes the methodology that we get in ordering stations creates some very unbalanced workstations. So if we look at this example here and we do our ranked positional weight method, we can see that the station times are very unbalanced. One way in which we can solve this is that we can rearrange our work elements, that even though this workstation would then exceed our cycle time of 1 minute, we could just create 2 parallel workstations of that group of work elements, and so we would then be able to double our cycle time and fit in the requirement, and then in this way we could much more easily, much better balance the line. Now I won't go into the theory behind this workstation, nor really the mathematics behind solving these problems, but you should just understand the general idea of doubling the cycle time for parallel workstations, and that this can be applied to just one work element. So if one of our work elements is vastly greater than the rest of our work elements in terms of time required, so let's say that work element 1 actually requires 2 minutes all by itself, then we could still group these all together and we could have 2 workstations simply doing work element 1, and then we could still retain our cycle time of 1 minute.